Hello calculus students, here are 11.4 inverse trig functions differentiation. Let's first of all where these come from. Y equals inverse arc sine of x, which means the same thing as the inverse sine of x. So you get sine y equals x, and now we can do implicit differentiation to figure out what this derivative is. So I took the derivative of both sides with respect to x at both sides. So the derivative of the sine is the cosine. Then notice you get dy dx because you have to take the derivative of the inner function. The derivative with respect to x of x is just 1. So we get dy dx equals 1 over cosine y. Thing is though, remember sine y was equal to x, and if we set up a diagram and look at the angle y, the sine of y, so katoa, sine is opposite over hypotenuse. So let's just call this x over 1. And so now we can use the Pythagorean theorem to get the square root of 1 minus x squared for this other side. That means the cosine of y is equal to adjacent over hypotenuse square root of 1 minus x squared over 1. Or square root of 1 minus x squared. So we get the answer is 1 over the square root of 1 minus x squared. So this is part of our whole list of derivative rules for the inverse sine. It's our last batch of derivative rules, the derivative of each of the inverse trig functions. And this is going to lead to an advantage later on in integration because notice here, if you got u squared, you don't have the derivative of u handy up here as 2u prime. You only have u prime. So we can't do just a usual substitution for that, but now we've got the arc sine, you can. So let's just apply these derivative rules. Notice in each case here, the derivative of the arc sine of 2x tan 3x, inverse sine of square root of x, arc sine of e to the 2x. Notice what's on the top here. And each time, that's the derivative of the inner function, the u prime you see here in all the derivative rules. And the bottom then is the square root of 1 minus u squared, and it varies depending on which one you're looking at, arc tan or arc secant and so forth. Notice this absolute value does show up in the arc secant and the arc cosecant. It's not necessary in this one because e to the 2x is always a positive number. So let's differentiate the arc sine of x plus x times the square root of 1 minus x squared. So the derivative, we just showed the derivative of the arc sine is 1 over the square root of 1 minus x squared. Plus, now we have to use product rule on this. That'll be x times the derivative of this thing. Well, it's a square root. Remember how that's 1 over twice that same square root? But then we also have to multiply by the derivative of the inner function, which is negative 2x. Now the other part of the product rule is just take the derivative of the x, which is 1, and leave the square root of 1 minus x squared alone. So let's see what we got here. We got 1 over the square root of 1 minus x squared plus negative 2x squared over 2, so that's going to be a negative x squared over the square root of 1 minus x squared plus the square root of 1 minus x squared. Well, these two add up into 1 minus x squared over the square root of 1 minus x squared plus the square root of 1 minus x squared. And anything divided by its own square root is itself, is its square root again. Like 3 divided by the square root of 3 is the square root of 3. So we just get 2 of these bad boys. 2 square root of 1 minus x squared. Okay? Let's check this on our TI-89. See what it does with the derivative of this huge expression. Okay, did in the calculator, and the calculator gave square root of 1 minus x squared plus 1 minus x squared over the square root of 1 minus x squared. But the whole point of this section is that derivative that can be simplified. This should be viewed as square root of 1 minus x squared again. And you get 2 square root of 1 minus x squared. So that's the answer I'm accepting. Okay? One of the drawbacks of the calculator. Analyze the graph of this. Arctan quantity squared. Wow. So, let's take a look. We can look at its derivative. We can look at what it looks like on the calculator and so forth. So, I'm actually going to get a rough sketch off of my TI-89 and see what we get from that. Because that's what a lot of you used to. As opposed. Okay, on my TI-89 in Zoom Standard, I'm getting something that looks like this. Let's see. comes dipping down and hits here at 0 and then comes back up again. That's just a rough sketch. So I suspect there may be a horizontal asymptote here. We'll look into that. Maybe not. But definitely looks like there's a min here, and also we suspect some inflection points. So I want to look at both the first and the second derivative of this thing. There's the second derivative. Let's get started on the first derivative. So for y prime, if y equals the inverse tan of x squared, the derivative then will be twice the inverse tan of x squared times the derivative of the inverse tan. And remember what that was? Let's go back. I think it's 1 plus 1 over x squared. Oopsie. Yep, there it is. Derivative of the inverse tan, 1 over 1 plus x squared. 1 over 1 plus x squared. So that's what we got. The derivative is 2 all over inverse tan of x squared all over 1 minus x squared. So what's going to happen with this now? We've got division by 0 at x equals 1, so that seems kind of strange that nothing strange didn't happen over here. I'm going to check on the calculator to see what it says the value to trace it at 1. Oh, it shows up as a point, 0.616. Something. Oh, it's 1 plus. I'm sorry, it's 1 plus. 1 over 1 plus x squared for the derivative. There you go. So we have no way of making the derivative undefined, and that looks consistent with our graph, no vertical asymptotes. Can we make the derivative equal to 0? Can we set 2 inverse tan of x squared equal to 0? When is the inverse tan of x equal to 0? When do you get a slope of 0 equals tan 0, and the tan of 0 is 0. So we just get our one critical number at 0 here. Now we can use the second derivative to decide if that's a max or min. Visually you can see that's a minimum. But we're also interested in the inflection point, so let's go ahead and do the second derivative. Here's the work for the second derivative and get this big expression. Remember, there was our first derivative. Bottom times the derivative of the top, minus the top times the derivative of the bottom over the bottom squared. And you get all that. And again, we can see what happens at x equals 0. What is y double prime at 0? And that's equal to 2 times 1 minus 2 times 0 times the inverse tan of 0. That's 0 as well, all over 1 plus 0 squared. So you get 2 all over 1, 2. So that means we have a relative min at x equals 0. Now what about those inflection points? Let's set the derivative, the second derivative, equal to 0. And we end up with 2 times 1 minus 2x arctan x equal to 0. This one's going to be maybe too hard for us to solve because 2 can't equal 0. 1 minus 2x inverse tan of x equal to 0. And we get 1 equals 2x inverse tan of x. Yeah, when you've got variables both inside and outside the tan, the trig function. Let's just go to the solver on the calculator on this one. Solver gives me two answers, and I get x equals negative 0.765 about, or x equals 0.765. So there's that symmetry we observed in our original sketch. And we can check the values at 0 itself. Oh, this is y prime of x equals 0. At 0, if we put 0 into the derivative, or into the second derivative, we end up with a positive number. So it definitely is concave up at 0. And if we put huge numbers in here, we'll end up eventually getting this thing negative, and so it's concave down on either side of these. So in between these two, it's concave up. So we do get inflection points there. And here's the results on our graph. There are the inflection points at about 0.7, negative 0.7. And now, does it have a horizontal asymptote? Text claims that y equals pi squared over 4. As x goes to infinity, these slopes that we saw originally, where's our derivative? The derivative is right here. this will grow faster than the inverse tan being squared, and so this is approaching 0. In fact, the inverse tan of x just stays between -1 and 1. I'm sorry, between -pi/2 and pi/2. So this is basically going to stay restricted, but this keeps growing. So the slopes do approach 0 as we suspected. Now, how do we get that horizontal asymptote? What is the limit as that goes to infinity? Well, that's some pretty sophisticated calculus, but we can check it on our T89. We can ask it, what's the limit as x goes to infinity of our function, which is y1 of x. So go to your calc menu, LIM, y1 of x, x going to infinity. Let's see what it says. Sure enough, the calculator agrees, and it says the limit is pi squared over 4. It also gives you the same answer for going to negative infinity. So there's your horizontal asymptote, points of inflection. You get a minimum here at 0, 0. There we go. And here's your differentiation rules for all the functions we've looked at this year. Those are the ones we talked about last chapter, and now we've added all these trig ones from this chapter. It's definitely something you want to have on your formula sheet if you're doing the derivative sections. Okay, flange out.